Sweet. And we're gonna really hope that this sounds okay, is what we're gonna do. I'll talk loud. So Russell told y'all that there's not gonna be name, current divider, or voltage divider on the exam. Sweet. That leaves pretty much 4 things that you've covered. And that's it. And so those are, and these are pretty much what's going to be on the exam. Resistance combinations. It is source dominance. Source transformation. And MAME. And I go ahead and write this down so people, whenever they come in, they don't have to ask again. So I have 3 problems because one of them combines source dominance and source transformation. And I'm hoping that y'all feel pretty good about resistance combination. Okay, good. We'll touch on that just for a second. Which do y'all feel that you want to go over in more detail? Source dominance / transform or MAME?
One thing for me is MAME when it comes to like infinite sources.
Cool. We'll definitely have a good MAME problem. And then we'll go over some basics of the source transform for sure. And source dominance. I have a good problem. The other thing I was going to say, and thank you, everybody gets more out of this whenever you participate. And so just want to say that. So we'll start with our lovely resistance problems and just go from there. So when you see this, let's first read the question, right? The network shown in figure 1, this is clear, right? Okay, cool. Contains a collection of resistors in series and parallel connections. Network is connected at terminals A to B. Calculate the value and terminal resistance at A to B, which is RAB. What do y'all see first? What sticks out? These nodes, A to B. That's weird, right? He doesn't give you that too much. So whenever you see nodes, and this goes from either if they're in the middle or if they're on the outside, you want to start the problem, start the combinations as far away from the nodes as possible. So if the nodes are like over here, and this is for resistance, this is for source transformation, this is for everything, you want to start over here. You do not want to start at the nodes because nothing is going to be directly in series with this. Does that make sense? Do you want me to say that again? Okay. From the terminals, if there was a hypothetical resistor here, that is not in series with anything. Same if it was here. This is not in series because those are isolated terminals. Also, just general question, what does it mean? What would those terminals be? Yes. So they can be probes. It also can be that there is an entire circuit connected there. You can have it be a terminal load, and that is where your actual stuff plugs in. That's where your capacitor resistance blob gets plugged in there. So you cannot assume that there is only one element. And that's why it cannot be in series. So there's just a brief overview. So like I said, you want to start as far away and work towards them. So do we want to start on this side or that side, left or right? Yeah, so for this one, you're going to start over here. We can start on the left and then work in to the terminals. And then we're going to go and jump over here and work our way in because we need our final answer to be from A to B, which when we see this, the other thing that we should see is we pretty much have two networks. We have one network over here and we have one network over here. In relation to these terminals, are those in series or parallel? Where the terminals are between A and B is network. So this is network 1. This is network 2. Are N1 and N2 in series or parallel? They're in parallel. And that is because we are looking from terminal A to terminal B. If we added them in series, we get rid of those nodes. We can't find that anymore. That kind of makes sense? Okay. So we see that N1 and it is in parallel with N2. Y'all know that annotation, right? Easy way to write it for the exam or homework. So we said we're going to start with N1 first, right? So R1 is R1 and R2 in series or parallel? Yep. So R1 plus R2. Is that in series with R3? Those are in parallel. And it's easier to see. Let's go ahead and combine R1. And for the exam, you don't need to draw it every step of the way. And I'll confirm that with your TA, but just make sure you show your work enough, like you say this, and then you say next, that is in parallel. Don't just do everything and write down the answer. But you don't need to do what I'm about to do. So what does that equal to? 13 plus 11. 24K. So then, okay, so this is where they're connected, right? I should do that. So by definition, hmm? They are connected at the same node. They share one common node, and that node is not connected to anything else. So if they are touching, right, only once, so not if both nodes are touching. If only one node is touching and there is not anything else connected, that is how they're in series. So they're touching here. They're not touching on the other side, right? And so there's nothing else there. That's how these are in series.
Like nothing else behind them?
No, so like if at this node there was something else.
Yeah.
So if this were here, they would not be in series. So now we see that that's 24K, right? Okay, so then we see, let's draw it like this. Do we agree that we can draw this like that?
I can see why it's in series now too, like when it's drawn like that.
So that's another good thing. Whenever we see triangles, triangles aren't super fun to work with. But luckily, whenever there's a node, if we have nodes, we can always add wires. We can always kind of take stuff and like stretch it out. So if we have this node, we can actually pull this over and just stretch it out. And so that R2 is now connected like this. Do you see that? How now it's a nice square and it's easier to see that they're in series. So
So R1 would also be in series with R3, right? So could those just add together and then? combine
Are they?
Or are they not?
So the R1 and R3 are connected here, right? Is there anything else connected there? So since there's something else connected there, they're not in series. And you can see it more clearly here. Right? So this is R1, 2, this is R3. Do they still look like they're in series here? Right. So what's next? Well, which is equal to, what was that, 12? I can't do math in my head. And I don't ever recommend doing math in your head because that is the silliest way to lose points.
Oh, yeah, there's.
Is 12? Okay. But don't do it in your head. So now let's go ahead and write this. Whatever. So now we have this. My resistors are not pretty, but I'm trying to draw them fast. So we just drew R3, this combination, and R4. We could draw the next one like this, but instead, I'm going to pull it out like I just did earlier. I'm going to say there's a wire here. We're going to take this and pull it over so that this resistor is straight up and down. But there's only a wire here. That is not where the 24K is. So I'm going to pull this over and put R5 here. And then up here, 18K is touching A, right? So this node that we just drew here, sorry, let me, R4, R5. Okay. So this is node A. Do y'all see that? However, this is not node B. There is another terminal here. There's another resistor here. Right? Okay. So now what's our next step? And that is going to equal 12 plus 18. So then 30K, and then is that series or parallel with R5? Great. R5 is 7.5, which someone's going to need to do. I definitely can't do that in my head. Point something.
Yeah.
Just straight up 6. Cool. 6K. Don't forget to keep your Ks on there, by the way. If you stop drawing them, just at least at the end, make sure they're there. So that's 6K. And then from A to B, we have this is 6K, this 24. So what do we have here? So from A to B, is 30. So now this is the left side of the equation. What we're going to do is now we're going to work from the other way. Because like I said, nothing is going to be in series with that. Otherwise, you get rid of the termites. So now we're going to do the other side super duper quick because we basically just did it. So this is going to be 24 in parallel with 12, right? So that's 24 in parallel with 12, which 8. 8K, then 8K plus 7.5 is 15.5, right? And then we have 15.5 in parallel with 30. Just go for it. Okay, 10.2, okay. Also, how many, don't round to only one decimal place.
10.21.
Okay, I like that better. 219. Again, I'm not grading. My general rule of thumb is do 3 decimal places. It's a pretty happy medium. So then it's 10.219 plus 2K, 12.219. Okay, so now we have A, we have B. And so now can we see a little better why they're in parallel? The bringing these out really helps. And so now here, we can just see 30K parallel with 2.19. So what's the total resistance? $8.68. That looks like the right answer.
Where's Peter?
I have it, but that's the right answer.
I was hoping it was like the word in the block regulation.
Oh, no. I've worked all these and that is about the right answer, so it's the right answer. It's about what I remember, if that makes sense.
Yeah.
Okay, so resistor problem, do we have any other questions? That's a good question. It's nice to think they've given questions before where they've given, instead of just giving you all of the resistors, they've given the boxes. And so just see how the boxes are connected, right? So just see if you have, like, say, one box. My boxes are too ugly for you to see what's going on. So is N1 and N2, are N1 and N2 in series or parallel? You can follow the path too, right? So you could also say, okay, this is coming in and then going out, coming in and going out. That's only one line. That's series.
So is it a good rule of thumb, like, if you can start from one node to another and go and draw a line about like lifting the pencil? In series?
Yes, but if you ever intersect a place where there's another line, they're not. So if there was something here, which that's dumb, there would never be, but now they're not in series, right? Because
You have to, like, go up and down.
yeah, because then you could branch there. This is just hypotheticals.
That also wouldn't be parallel.
Correct.
Okay.
This would be,
So just, yeah, branch.
yeah, but they're not in series or parallel there. But that is more of a hypothetical good thing to know. I'm trying to figure out which one I want to do next. Let's do MAME next. And let's just jump straight in. So read the question, right? Always read the question. Most important thing. The resistive network shown in figure 4 contains a voltage-controlled voltage source and a current-controlled voltage source. Doesn't really mean much. It's just him telling you what they're made of. The meshes are ordered with the circled numbers. Using component values as shown, you are asked to do the following. Write out fully the mesh analysis matrix equation, MAME, in numerical form. Express this equation in the usual format of that, where IM contains the mesh currents, IM1 through IM4. Solve MAME for the mesh currents. I will tell you, and I hope if people watch the recording, if it says to use MAME, you have to use MAME. You cannot use KVL. Yeah, it's not my favorite thing. It's just so many equations. There was another part to this problem, but we're not going to do it on this problem, which is why it says following. But let's just go through MAME. I'm just gonna basically teach it right now because I haven't taught it to any of y'all yet because I haven't seen it. So how many meshes are there? There are 4. How big is our matrix gonna be? Exactly. So we have a matrix that is an n by n. And how many of y'all are in what's his face's class? Spangler? Are y'all all in Spanglers? Fake Diffie Q. Y'all haven't gotten to matrices yet, right? Cool. Do y'all know much about matrices? Ish. Y'all know multiplication at all?
I've never taken a different class.
Cool. It's actually linear algebra.
Or no.
All good. I'm gonna teach it today then, is what we're gonna do. Okay, so this is how I write it out, just for ease of solving MAME. This is n by n, and this actually is correct, actually. So this element is n 1 1, because this is column 1 2 3 4, and this is row 1 2 3 4. And I did not write it big enough. So this is n1, and we always go row then column. Always. Just got to remember that. So this is n1 2, this is n1 3, and this is n1 4. Then this is n2 1, n3 1, and 4 1. Same here. This is n2 2, n 4 4, dot dot dot, dot dot dot, dot dot dot. You get the gist, right? Okay. So these rows are meshes. This is going to be equated and thought of as mesh 1, mesh 2, mesh 3, and mesh 4. Not too bad to remember, right? So how we fill this in is all of the diagonal elements, which he always uses, Diagonal is literally this diagonal where it's 1, 1, 2, 2, 3, 3, where it's the same row as it is the column. Those values. Number 1, those values, right over here. They are all positive, and they are the sum of all of the resistances in the mesh. Okay, so they are the sum of R's. Sum. And then the off diagonal, which what's that? Yes, but literally in the mesh. It's a trick question. Everything that isn't the diagonal is off diagonal. That's all that means. So the off diagonal, they are all negative. Always. They're always negative. That's all you need to remember. And they are what is shared between the subscript row. I'm gonna just write this. Show. I said shared between subscript, row, and column mesh. What I mean by that is if you are on mesh 1, mesh N1, 2 is going to be what's shared between mesh 1 and mesh 2. Mesh 1 and 3. Down here, this last one would be 2 and 4. So you're going to go down all of these and just see what is shared. Now, is N41 different than 1,4? No. So you only have to do this once, and then you can just flip it. And the way I do it is I go across, and then I go down, across, down, across, down, and I'll do that. But I hope that that makes some more sense about how to fill in the resistive matrix. And then on the other side, so then this is multiplied by IM1, IM2, which I didn't do that right. So that's what it is, and that's what it is up here. But this is multiplied. Now, I didn't say it at the beginning, but I can say it now. The way that matrix multiplication works, there's rules, but you're only going to ever need this. This row, if these two are multiplied together, the first row goes to the first column. Whenever you multiply here, IM2 goes to the second column. IM3 here, IM4. And that is why they're shared. There's a long derivation from KVL, KCL. If you really want, I can show it to you. But this is all we need right now. I would show it to you later. So that is why they're mesh 1 shared with the current of the mesh 2. I'm going very slow just for this one. On the other side, we see that it is EM. Oops. So over here, I'm going to write that it is supposed to be, hello, yeah, the sum of all voltage rises. Okay, so over here, as we go, you're fine, go around for mesh 1, 2, 3, 4. Thank you. It is going to be the sum of all voltage rises. Have y'all been confused as why it's rises here and not drops? Because normally it's drops, right? Okay. Right? So whenever normally it's the sum, this is KVL, of all voltage drops equals 0, right? Well, all we do here, there is a big equals sign here. This is just an algebra equation. All we've done is taken the voltage drops and moved them over to the other side of the equation. So normally voltage drops are positive, right? All we've done is we've taken a voltage drop, positive voltage drop, and moved it over and subtracted it. So now, instead of it being positive voltage drop, over here, it's positive voltage rises. That is why there rises over there. It's just an algebra equation. We moved it to the other side of the equal sign. Sweet? Sweet. So here, and then is going from positive to negative, like this, a voltage drop or rise. Right. Voltage rise would be here if you were going from negative to positive. So every time you see a source, if you go from positive to negative, it's going to be, so is it going to be positive or negative here? Perfect. And then the other way around. So now let's actually do it. I'm just gonna get another page and we're gonna do the problem. I get to where I can see. So let's go ahead and start with our resistive matrix. This is mesh 1. Oh, very, very important. Always clockwise. Always. 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 Right? Okay. I just had a like, right? And the reason is because it works out the signs and we're telling you, it could work with everything counterclockwise, but you would have to change. And for sake of keeping everyone's work the same, always clockwise on all of them. So 1, 1. What is the sum of the resistances in mesh 1? 14. Beautiful. So now, what's this next element going to be? Perfect. This is what is shared between mesh 1 and 2. What's shared between 1 and 3? 0, 1, and 4. Perfect. All right. -10, 0, and 0. Now mesh 2. What's the total resistances in mesh 2? Oh, I didn't even see that one. It is 24. It's 10, 20, 21, 24. Yeah. Okay, so now what's shared between 2 and 3? -10, -10, and then 2 and 4. -1. Okay, mesh 3. 17, and then 3 and 4. 2, -2, sum of everything in 4. 8. Perfect. And then this is IM1, 2, 3. And then eventually, if you feel comfortable doing this, you can just write IM until the end for time's sake. And I should have done this at the beginning. I should have gone over strategies of taking a Russell exam. After this problem, I will go into that.
You take it all, or take the rest, like the, his exams, or?
It will be a struggle for time. People finish, and this exam might not be as bad because it's pretty early on in the content, but by and large, as a rule, you have to time manage. Now that I'm here, I'll go ahead and do it. I highly recommend at the beginning of the exam, Russell's going to go through and read all of the questions. Start with the one that you are the most confident with. Do not start with the hardest one for you. Like, it might be that you are great with source transformation. Start with that one. Do the hardest one that you're going to struggle with the most last. Or if you want to go the other route and do the one that has the least amount of points last. Depends on how you want to min-max it, right? So that's that. And then show your work, but don't make it take you a super duper long time. Write out your steps, even if you don't redraw it every single time, because it's gonna be a struggle. And then get comfortable with your calculator. Get comfortable with matrices, and I don't know, for right now, it should be fine. If you don't have this guy, later on, it's gonna really hurt you if you don't. For probably like the second exam. So someone said in the Discord, and I haven't responded yet. You can also check these out. We have about 30 of them in IEEE. You can check them out for like days at a time. Like you're really supposed to come back every day and check it out again. You give your student ID and we let you sit. I recommend if you are in a position to afford one financially, which they're like 150 normally. Sometimes you can get them on Facebook Marketplace for like 80 or 70. 80 or 8? Okay.
What?
I was gonna be like that. You can do stuff like that. I recommend having one so you can take it home and really get comfortable with it, because if you haven't used them, it takes a minute. I'm gonna go over how to use it in the review today. But if you can't, we're college kids, right? We have them to rent out. But please, please, please do not come in here the day of and you've never used the calculator before and you try to do it for the first time during the test. It doesn't work out.
How much does it cost to rent it?
No. You don't pay us to rent it. You just give your student ID.
For the license, if anything that you need to
Yeah.
get that.
Yeah.
Okay. Isn't it the bottom, like,
This is take your time to start out like out. You might.
Mhm. So, and I'll go over tips and tricks for how to do things fast. And I say I like pushing the least amount of buttons to do a thing. I will show you how to do that. And then, yeah, that's the other thing. Okay, so it's open book, open notes, right?
Mhm.
I recommend writing out a cheat sheet. You can use all of your notes, you can look at the materials. You cannot watch videos, you cannot be on the internet. You can have your computer out, don't ruin it for everybody else. That's what I say. But I really recommend writing a cheat sheet that has everything you need on one page, right? I will mean you don't have to be flipping through everything. You have everything you need. If there's an emergency, you have everything else. But you have pretty much what you know you will need on 1 or 2 pages. So, my recommendation. I think I got everything. Okay. Back to the problem at hand. Let's do sum of all voltages. So now we have our big equal sign, and let's do mesh 1. What are all of the voltages? And we're just going to write them exactly how they are right now. So we have 1 voltage source, mu VA minus VB. Is that a drop or a rise? Can you see that?
Drop.
Perfect. So it's going to be negative mu VA minus VB. Now, that's everything, right? What about mesh 2? Anything else? Perfect. Minus 2. What about mesh 3? C. And then mesh 4? Okay, so we are going to treat this as an algebra equation, right? We have variables and we have numbers. Solve an algebra equation. You want to get all of the variables on one side of the equation and all of the normal pretty numbers on the other side. That is exactly what we're going to do here. We want to take in this matrix all of the whole numbers out and keep them on that side of the equation, and then make it so that we can move all of the variables to the other side. So let's do the easy part first. What is the independent matrix going to be? So all of the whole numbers. Is that a whole number?
Of the dependent.
This is the independent one.
The independent, the one that's diamond shape or triple.
Ones that don't have like the RM or mu or anything.
Oh, okay.
So this is a variable essentially, right? We're going to have to plug in our IM1s to find this. We don't know that. So we're going to do the numbers that we for sure know, which there's nothing there, -2, nothing there, 2. Happy, pretty numbers. Now we have the other stuff. So I'll just write it over here, maybe. And these are added together, right? Cool. So negative mu VA minus VB, and I am just writing out every step. Mu. Oh, and that's the other thing. Make sure you like show us that you know what you're doing and you're not copying the answer. After that, show as much work as you need to get it right. If it helps you writing out every single step, write out every single step. But you know yourself much better. And so do what you know will work. Capiche? Cool. So now is the tricky part. We need to get these guys to the other side of the equation. How do we do that? Perfect. So we have essentially 3 unknowns, right? We have, well, other than our IMs. In terms of these dependent sources, we have VA, we have VB, and we have IC. And these are all, they don't look like it, but when multiplied by RM, I'm giving it away. Hold on, I'm giving it away. Ignore the fact that that's a current. These are all voltages, right? Just ignore that fact right there. Yeah, and that's why it's multiplied by Rm, by the way. Fun fact. These are all voltages on this side of the equation. How do we get a voltage? Are these voltages? So that's the fun thing that's hard to see. This, when multiplied together, is a voltage, which equals voltage, right? So all we need to do now is go the other way. We want to change these voltages, because we agreed those are voltages, into a matrix of resistances multiplied by a mesh current vector. That's all we're doing. We're just trying to be able to subtract it. It's all just algebra, all algebra. Where's my poster? Where is this? To do that, this is our actual variable, right? This is our x, is our IM1s. We need to write these dependent guys in terms, right? In terms of IM1, IM2, IM3, IM4. Does that part make sense? Okay. So let's look and let's find all of our VAs and VBs and such. Okay. So cool. So let's do the easiest one first. And I'll tell you why it's the easiest one. Whenever it comes to MAME, these are mesh currents, right? So finding currents in terms of mesh currents is a lot easier, right? Than finding voltages in terms of mesh currents. Right? Okay. So IC, where? Yes, IC. All we need to do here is we need to figure out what that current is equal to in terms of all of the other things, right? I'm repeating myself over and over, but I want it to be really clear what we're doing. So we are looking for specifically the current in this branch from this point. So let's see what currents are flowing through this branch. That's all we're doing. And for now, we're going to just test it. Is mesh 1, IM1, flowing through that?
Yes.
Is it flowing in the same direction or the opposite direction? So is it going to be positive or negative? Perfect. So it is going to be IC is equal to IM1. And then what else is flowing through it? Perfect. So is it flowing in the same or opposite? So minus IM4. IM4. That one, super simple. So we like that one. Now for the other ones. VA and VB. Can't.
Does VB important at all, or is it just like ground?
V.
Is it VB?
Yes. So wait. Oh, down there. I cut out that part of the problem because I wanted to keep it simpler.
So
Those are the problem with like UV, etc.
Not quite. So this is part A. There was a part B that said use these meshes to find the difference between VA and VD. And so it wanted you to take it and find from there. But I wanted to make sure I got to everything because my reviews always take forever. And so I cut that out. But I'm here for as long as you want me here. But people always watch my reviews on like 2.5 times speed.
Oh, we're just-
They're on the HKN teams. Teams,
oh, but-
yes.
That on the Discord too, but it's changed.
We don't have an HKN Discord. It's on the IEEE Discord, yes. But, let's go ahead and come back to VA. So how do we find voltage in terms of current? So our lovely V equals IR. I write it on every single problem ever. V equals IR. We live by it. Electrical engineering's favorite equation. So we're looking for VA. We're going to write it in terms of our currents. On this specific problem, he only gave us he only gave us a point, which is kind of gross. But we can still do it. It's just a little gross. So the other way that we can find voltages is voltages kind of don't exist. They only exist with a reference to something. They exist, but without a ground reference. They're only sort of a thing, right? So in reference to 0, which is why they're in every single problem, in every single application, you will always have ground. And so with that, whenever we're looking for a voltage, we're always looking for it with respect to ground. And node voltages, whenever you get into name, you're going to do between 2 nodes. You're looking for the voltage between 2 nodes. We could do that on this problem too. We could just do it, but then you would have to find like more than 1 node. So whenever it comes to here, we're going to look with respect to ground. Does that make sense? Sort of. Let's do it. So VA, this is the easier one. VA is at this node. Where would be the easiest way to find VA? So voltage VA minus 0. Let me put it this way. Let's draw VA as positive, right? So this is what we're looking for, because we're looking for a voltage drop. Ground is negative. Do we agree with that? So this voltage drop here is what I just wrote. VA minus 0, which is how we would solve for VA. How can we find that? Mhm. Almost. The only issue with that is exactly correct. Only issue with that is what way is the current flowing? So we'll go ahead and draw our current polarity. This is super important. This is our current polarity. And we agree that whenever current flows into a resistor, that is the drop. It's passive, it will always be that with respect to a current. Yeah. So, but we are looking for VA. So this that we're trying to find is that. Are those in the same polarity or opposite polarities. So it's going to be negative. Kind of makes sense. Okay, we'll do it on the other one too. Mhm. So if you were like proper reading on it, that was probably a little high level for this class, to be honest. It's not, we don't need to do it too complicated of a manner, if that makes sense. We're looking more, if we can just see this and see that this is VA minus 0, and then see that this is the voltage over this resistor, that's pretty much good. As long as we have a node voltage at ground, it's fine. That's like, I think what you're talking about is some pretty high level stuff. Was that in the materials? That's fair, that's impressive. But okay, VA. What did we say VA was equal to? Positive or negative? Negative. IM1 times R1. And now the little bit trickier one. So next we need VB. But remember how I said that if we found it here, that's not quite enough, right? If we just found from VB to this point, is that point equal to 0? So if we found just this voltage, we would need to find another voltage. We would also need to find VD. Easier way you can do this is you can just say, okay, let's take from VB, have that be positive, and ground is negative. Now, to find the path, the voltage over a path that is not just one element, you're going to draw a line. That's how I do it, at least. You're going to draw a line from the positive terminal to the negative terminal and add up the sum of all the resistances. That is how you did that one question that everybody has a heart attack over on your second problem set, where the EG is over the two things. That is how you should solve it, is draw a line. It's okay. It's a rough one. So do we want to go this way or do we want to go this way? Yeah, take the simplest way. That's all I can say on that one. So we're going to come this way, and we always go from positive to negative, right? Why? Yes. Yes. The combination of both of those. It is because current is always going to flow from positive to negative. And then the positive is always going to be the highest. So if we know that positive point is the highest, then we know it's going to flow from positive to negative. And that's why we're also going to say it's VB minus, I never write in pencil, so I'm bad at it, VB minus 0. The bigger one, the one at the positive side, is always going to be first. And the other thing that trips up everyone is in this equation specifically, it is the sum of all voltage rises. But whenever we are writing out our equations, it goes back to voltage drops are positive, which sucks, but that's just what we have to remember. So this is the outlier where voltage rises are positive. But whenever we come back over here, the drop is positive. Yeah, you're good. So in this algebra equation, we moved over are positive voltage drops and they became negative, which is the same as all the voltage rises are positive. However, passive sign convention still exists and all voltage drops are positive. So whenever we are writing out our equations for dependence, they are positive voltage drops. One more time. Whenever we write out voltage drops like over resistors, right? Is a voltage drop positive or is a voltage rise positive? Yes. Voltage drops are positive, which is positive and negative, because that's voltage drop. So typically, passive sign convention says that that is a positive, and rises are negative. So whenever we are looking for dependent sources, we come back to, we are looking for positive voltage drops. Goodish. Okay. So come back over here, VB minus 0 is equal to VB. We're in out of space again. So I'm gonna go like this is negative. We already wrote that. So VB, let's take the path, right? What is, just like conceptually, what is the voltage VB? I'll lead you there. It is the voltage drop over this resistor plus voltage drop over this resistor, right? Superposition, linearity, whatever it's called. And then as for the signs, right? This is positive, which means that the voltage drop over that is going to be negative there, right? That makes sense. Right? This is, yeah. So VB is positive because we're saying that VB is higher than 0. So we're going to write our positive there. Whenever we go over the resistor, it's going to be a drop from positive to negative because we want to maintain that. Now let's come over to this resistor. We're already given that it should end at negative. So do we agree that the voltage drop should be like that? Okay, so that means that it's going to be a sum of that plus that. So those are both voltage drops. And that is how we are denoting the polarity of what we're looking for. Okay, let's figure it out. So is there 1 or 2 currents flowing through that resistor? So the voltage has to be both of them. So this current over here is going that way, right? And then this current is going that way. We agree? Okay, so what's the voltage over R7? Perfect. Does everybody agree with that? Okay, that was a hard one. Now what's over R5? Perfect. So make sure whenever you're writing these, write out these equations on your exam, please. But now we have all of our variables, so we can plug them in. I'm just going to write it out one more time for the sake of visualization. So all I'm going to do is take this, that, and put in these equations. If you are fine with doing numbers immediately, do that. I am just going to go ahead and do them and then put in numbers. So negative mu, so we have negative mu times big parentheses. Make sure you write your parentheses if you have a variable and then subtraction. So big mu times R7 times IM2 minus IM3 plus 5 times IM2. Yeah. Those too many parentheses. And then next one, we have positive mu 7. Also, if I make a mistake, please call me out. Then we have negative, and then this is negative, right? So you have negative, negative, turns into RM, I see. And then this one is negative RM. And I immediately just, that's not what I want. Okay. That's still a bunch of things. We need to put numbers in now. So mu is 5 and RM is 2. So
Why did the sign split? Oh, you did right. Isn't it, IT, isn't IT and positive? Cause you wrote, I don't think you switched the sign, cause IT, there's no negative there.
oh, I totally messed up.
I think you signed for VA, but.
Oh.
For VC, I mean, I can. Right?
Yeah, no, and I messed up another part too. Jeez. I just did VB. I didn't even do VA. I left out VA. I want y'all to catch me. You did. I appreciate you. So then, and then it's negative again. It was going to be too rough to try to mix up all the signs. It was just going to get confusing. Okay, so it's mu and then VA minus VB. So negative mu times negative IM1 times R1 minus R7 times IM2 minus IM3 plus R5 IM2. Parentheses, lots of parentheses. And this is where, like I said, if you want to plug in numbers straight away, you can, but I'm just writing it out so that you can see why. I don't know if that's the right number of parentheses, but we're just gonna go with it. So what we're gonna do now is we're going to We're just gonna plug in numbers first. So, do you mind if I go ahead and distribute though? So we have 5, so we have -5 times -4 IM1, right? Minus that makes sense. Negative or 7. Now that you can see the numbers times 6.
The top paper below like the top one below the,
I didn't know if y'all still wanted to see that. The actual thingy. Because I don't know what R5, like,
well, I think you could put the, not the one you're working on, but the one with the circuit, you could put that one on top.
but I need this
Oh,
is the issue. I need that and I need that. -5 times 3. Pretty sure that's right. Cool. RM is 2. So then we just have 2 IM1 minus plus 2 IM4. Then we have IM1 minus IM4. Gross. But we're here. What's the next step?
That has.
Okay. So you make a new matrix.
Like, one is like a column vector that's like IM1 through 4, and the rest is like only coefficients.
Exactly. We want to subtract this to that side, right? To do that, we have to make it look like that. So we need it to be in terms of our IM vector and a 4x4 resistive matrix. To do that, you do exactly what they said. We're just gonna do it down, and then we remember that this is mesh 1, mesh 2, mesh 3, 1, 2, 3, 4. We're gonna do the same thing that we did earlier. This is gonna be IM1, IM2, IM3, IM4. So in mesh 1, what we're gonna do is we're gonna say how many IM1, 2, 3s, and 4s are there. And then we're going to take those coefficients and put them in the 4x4 matrix. That is how and why, because we are multiplying it. IM1, 2, 4. So, how many IM1s are in the first row?
Oh,
Row.
sorry, row.
times negative 5.
So
Positive.
20.
You're good. So we have 20. Now, what about IM2? Negative 15. Yeah, because it's minus 30, right? We have negative 15 minus 30 is negative 45. Now, what about IM3s? Negative 5 times 6 times negative IM3. That's 30. Any IM4s? 0. Ah, crap. Good catch. No. Good catch. Good catch.
So do you think it's valid for kids? Right.
Yes. Positive. Right. And this one's going to be the exact opposite. Negative 20. And then we have negative 30 plus 15. So negative 15. And then we have positive 30. 0. These are easier. How many IM1s? Negative 2. Beautiful, right? Okay. Lovely. So now, what's our next step? Perfect. We want to get these numbers to the left side of the equation. So what I do is I draw a big friendly arrow and say subtract to show your work that you're subtracting, right? So can I get everything in there? Ish. So if you don't want to do it in your head, don't do it in your head, but I think we're going to do it in our heads for today. So 14 minus 20, right? What's that? Negative 6. Now, negative 10 minus 15. 5, 0 minus negative 30. 30, 0 minus 0. Yay. Now, next row. Negative 10 minus negative 20.
This is a review for circuit one.
Come on in. So now we have 24 minus negative 15. 39. Yeah. Then negative 10 minus 30. 40, negative 1 minus 0. It's negative 1. 0 minus negative 2. 2, negative 10, 17, then 2, negative 2 minus 2. Negative 4. Perfect. Then we have 0 minus 2. And those stay the same. You can't see what I'm writing, but that's more important. And then 8 minus negative 2. Beautiful. And now we have this whole thing multiplied by IM 1, 2, 3, 4. What is this equal to? Perfect. Right up to there that we did forever ago. 0, negative 2, 0, 2. Now from here, we let our calculator do all the work because there is not enough time to do that on an exam. And it's gross, and I don't know why you would want to. Now we're going to go over how this calculator works. If you have the other calculator, you can do that. I am not very good at it.
We're gonna have to use a computer algebra.
What do you mean? Oh, the CAS?
We're gonna have to use that in this.
Specifically this exam, that is unlikely. I do not have the questions right now.
Oh, yeah, I'm asking because I don't have one of those, I have a calculator, I have like a TI-84, which can do matrix operations, but not like, it can't do it doesn't have a computer it doesn't have a calculator system.
For at least the next test or the final, it is likely that you will have to use it at least once. I don't know exactly when. For that first problem on your problem set, you had to use that, right?
Indeed.
Um,
Also, you guys do rentals, right?
and so you just come and you give your ID. If you're gonna do that, I highly recommend, before the exam, working on it and figuring out how to use it. And so, if y'all, we're right here, if y'all wanna go grab one, if you're planning on renting one, real quick, so you can follow along with me.
Is this test open now?
Yep.
You might want to close your laptop.
Oh my gosh, dang it. If you don't have it, no. We don't particularly like taking IDs. But we have taken that, like, we don't want to be liable for that, but we will 100%. Just make sure you come get it. Hello,
What's up?
it's my review.
So what?
My review.
Oh, you're not done yet?
No,
I thought you were. I mean, I thought you were putting everything like just to go.
no, I'm charging my laptop.
Okay, see you then. Talk to you later. You're good though?
Yeah.
Okay, see you.
Okay. Also, you just got here, this is what's gonna be on your.
Yeah.
And then you have to go, I assume.
Huh?
You have to go.
Yeah.
Okay, cool. I was just gonna say, we're doing another problem after this, but
Oh, no, we had all of it down for the most part.
Okay.
Just wanted to hear like. I think it's-
okay, cool. Okay,
Oh, those are the topics for sure.
he has before changed his mind and done other than what he has said. So if, don't come mad at me and sue me. But
Haven't really done
What
it
he's-
yourself.
yeah, pretty much. So,
The battery thing. Yeah, the parallel battery thing, how many batteries do you need in order to get this? I don't think it's gonna be on, but it was like, I don't know, a tangent. We did talk about this thing where it was like, you can only put like,
I'm
like
sorry.
voltage sources that are, voltage sources that are like.
Hey, Josh.
In parallel, in your case,
that will more be under your final. Oh, my God. Or like for the concepts might be on your final exam. I will ask him if he's gonna, there is a problem, but I don't think so. We'll see, but for now. Yes, yes. Now. I'm trying to get the exposure right. Y'all kind of see that? Is that pretty good? Okay, so we're gonna start from. So from the home page, you can use the scratch pad calculate. There's not inherently stuff wrong with it, but really, I usually go to either new or current. So ignore that. If you come to new, you'll say add calculator. And this is how you get to your main screen.
Click the new, where in the menu is that exactly again? Oh. Right.
Or if you already have it open, you can go to current. And this will be recorded if you want to go back and watch it. So your normal calculator, and I'm gonna go super deep. Obviously, you have all of your numbers, control, and all of the blue gives you all the blue functions. So for example, if you want a square root, you're gonna do control to get that little button. See that? Okay.
Matrix.
So there are a couple ways to do matrices. The way that I normally do it is there's a function button here. This has a list of commonly used things. This is where if you want, you can do absolute value, you can do integrals, you can do derivatives, you can do sums. And then if you want a matrix, what you're going to click, unless you want a 2 by 2, 2 by 1, or a 1 by 2, you're going to do the 3 by 3. And that will take you to a custom matrix where you see how many rows and how many columns you want.
So where do you, find the function? The one that book.
No, the one next to it with the absolute value on it. And then
So wait, what is the button button again? That you go like that, you click inside there. No, you go, once you click the function button, what's up? Yeah, once you click that button.
the matrix, the 3 by 3 matrix.
Sorry, just a the document cam was a little bit blurry. Okay. So Ruby.
Okay, so from here, the buttons are a little less clear, but I think the screen is more clear. This is where you put in how many rows and columns you want, obviously. So for here, first we're gonna want a 4 by 4. So 4, and then to get to the next one, the easiest way is to hit tab. So I'm gonna go over both ways. So the first way I'm gonna go over is doing where you multiply by the inverse, right? So I'm gonna do a 4 by 4 matrix first for our resistive matrix. And then even once you're here, even if you're still in there, you can just hit enter and it does okay. And then once you're here, what we're gonna do is, can you see that? Beautiful. I'm gonna go ahead and hit all of the buttons. To get to the next one, hit tab. It makes it way easier. So we have -6, tab, -25, tab 30, 0, 10, 39, -40, -1, 2, 10, 17, -4, -2, -1, 2. Obviously, it's going to take y'all more time than that, but proof that you can get fast with it. Yeah. I've been using these since I was in 9th grade. We had these at my high school, so took me a minute. And so then once we're here, we're gonna hit the square root button, which you can kind of see. I actually lied. We're not going to do that. We're going to hit the caret button. Yes. So we do caret and then to the -1, like you said. And then we're going to multiply that and we're going to make another matrix, which I'll show you the other way to make a matrix now. So from menu, this is how you get to everything that you could want in the calculator. Most stuff. Takes you to a menu, shockingly. And then we're going to come down to matrix and vector. Now you can either go all the way down to it and then hit the arrow button, or if you want, you can just hit the number that's on it.
The menu, then go to matrix.
Yes. And then you can just hit create. So you can either arrow over to it, or if you want, you can just hit 1. And then, well, we're just, yeah. And then hit 1 again to make just a matrix. Takes you to the exact same menu that we got to before, but that's the other way to do it. And this one is going to be a 4 by 1. That. And then we're going to put in our sources. So we just have 0, -2, 0, 2. We hit enter. And that is our IAMS. Now, this is the mathematic, like that is what you learn way to do it. That's not how I do it. I do the augmented matrix, like he was saying before. So a lot of y'all have not taken linear algebra, so you probably don't know what this is. There's something called a row reduced echelon form. All that means is you get a matrix with only that diagonal. Everything else is a 0. And then it will know, and it basically tells you, okay, there is 1 of this column, and then it equals that. And then it equals y. And ... It's the exact same functionally as this. It just, like I said, is less buttons. So that's how I do it. So we can either come to menu, matrix and vector, like we said, and then 5 is that row reduced echelon form, right? So to the 5, we can just hit the number 5. All that does is give us the letters R, R, E, F. What you can also do, if you forget where that is type the letters on here, R, R, E, F, parentheses, and it will do the exact same thing. Which
The menu, vectors, and matrix. Keep it out of.
Control Enter. Very, very good question. If it gives you gross fractions, the little thing above Enter is squiggly lines, which you could almost see there. And that is approximate answer. So exact fractions, approximate decimals.
And then I assume we just would make a 4 by 5 augmented.
Exactly. So we're going to go back, make another matrix. We're going to do 4 rows. And then instead of 4 columns, we're going to do 5. And we're going to put that voltage independent mesh in that 5th row. Only thing we're going to do different. Otherwise, it's going to be the exact same, except now those 0, -2 is going to be in that 5th row. And you don't need to do it. I'm going to do it real quick to just show you that they give the same answer.
Oh, so
Yeah. So whichever is easier for you or whichever way you remember. This is the way that I do it because, like I said, it's
I'm gonna do the variable portion, I'm gonna make it equal to e.
Mhm.
How do you do the variable, take a variable?
Yes.
You just put like a value x.
Yeah. So, also super important, a couple things actually. If you want to delete everything you did, control, delete, gets rid of the entire thing, very helpful. And then if you want to bring this back, you can just arrow up and then hit enter, and it brings it back down to here. And then you can just change because you accidentally messed up a value. So here, if I wanted this to be x, you can use any variable. I might have x be something. No, I can just say x. This will now solve it. Gross. That's a really, really big number and disgusting, but it gives you this in terms of x. That is exactly how you would have done that homework problem. But I think that that one only had, yeah, zeros. So that's more what it should have looked like. It has parentheses.
So if you created the matrix, like let's say you created the matrix, let's use above,
Oh,
you get to the ROE.
yeah.
I just know that that's something I'm gonna absolutely do for at least one call.
So you would just do the typing it, RREF, or get it from the menu and then just do a parentheses. And then it'll do it. Oh, cool.
Is there a way to like?
That should be fine. This is coming back to what we were doing. This is your answer, which if you remember is the exact same as this one. Those are the exact same. The last column is your answer. So that is that. If you did need, with variables, some important things, I'm going to show you how I do it, and then I'll show you the other way how to do it. If you wanted to say, okay, now I'm going to try and have that X value we just made be 17. We're going to do X, and then there's this little like colon equals sign there. And so do that little colon equals sign, looks like that. And then 17. So now X is 17. Super duper important, especially if you're renting a calculator. If the variable is bolded like that instead of like that, it means that there's something stored in it. So if you're trying to use a calculator and you have something stored in it, it's going to give you a crazy answer, obviously. And you're going to do that for EMAG. Because EMAG does that a lot. So now let's try and do that augmented matrix again and see what we get. You see it's bolded and black. And so now it gives us real answers, real numbers. The other thing that we can do is if we had Y, yes, so that one is going to be menu, number, I lied, menu actions, and then delete variable, and then you can hit the variable you want to delete. You can also do actions and delete A to Z if you just want everything gone.
Action. Menu plus one plus multiple.
Delete variable.
We have to have a variable selected. How do we select the variable?
You just type the variable. Now say you wanted to solve for Y. Say you wanted that 9, you want to do 9 is equal to 18y plus 24. And you wanted to solve for y, right? What you're going to do is menu and then algebra, because it's an algebra equation, and solve, or just type solve. And then you're going to put that equation in there. And then very, very important, after you put the equation, comma, which is all the way down here at the bottom, comma, the variable you want to solve for. And now it gives you that y is equal to 833.333 times 10 to the negative 3. Which I keep mine in engineering notation. Oh, that's another super big thing. So under settings on the main page, this is, you only have to do it once. Document settings, this is where you change it from degree to radians when you'll need that. And this is where you can change your exponential format. So it can either give you just numbers with no decimal places. Like if it's like 10,000, it'll just give you 1,000,000 zeros. Scientific will just do 10 to the, we'll put it in scientific notation. Engineering notation is factors of 3. So it'll give you kilo, mega, giga. So, and you may have seen that that's what my calculator has been doing. It does times 10 to the negative 3. That's what the E is.
That's very convenient.
It is very convenient. And so, okay, that's everything with the calculator. That took longer than I was expecting. But that's everything you should need, that you'll need to know for this exam. We'll get into science, into complex numbers on the next review.
Eat those first.
Okay, now last problem. Okay. Just a resistance problem. So if you want to review, you can go watch it. I just went over kind of general things to know and tricks to look out for. And then if you want, just go watch it. Thank you. So source dominance, source transformation, and source combination. How'd y'all feel about these on the homework? Oh, it's super. Okay, that we did that.
Did it earlier.
Yes, that's fair. That's very fair. Y'all want this to be brighter?
A little bit.
Okay. I changed it for them. Oh, so read the question, please, always. Apply the theorems of source dominance, source transformation, and source combination to reduce the network shown in figure 3 to its minimal form with nodes 1 through 3 preserved by eliminating all redundant components. Draw the reduced network and use it to do the following. Calculate the node to ground voltages VN1, 2, and 3, and calculate the voltages VJ2 and the current IE2. Show your work, and you don't have to explain assumptions. It says that you don't have to explain assumptions. Joe said that earlier. So what is going to be the first step then?
Could change that. We could change J1 into a voltage source. I'm pretty sure that current is the dominance in theory, so then we can just get rid of everything except J2.
Perfect. And it also tells you in the problem which to do first, right? It gave you a hint.
Okay, that's where we should do it. Dominance.
So he gave you a hint on how to do it. It says first, draw it in its minimal form. Minimal form is both source transformation and source dominance, but realistically, it's mainly source dominance.
So it's like 7 and no equivalence basically.
Sort of, not quite. That's gonna be later on.
I mean, like, would those be an example of that?
Yes, that is an example of source combination.
That's
Yes. So very, very important rules on source dominance. Voltage dominates in and current dominates in
you.
perfect. However, voltage, very, very important, does not dominate in parallel if there is a resistor in series with it. There is a resistor in series with a voltage source. It does not dominate. That is important thing number one. And important thing number two is to do this, so to actually bring it back out and calculate currents or voltages over specific components, you have to bring it back to its original form. You can use source dominance to calculate node voltages as long as everything is preserved, like it says up here. But to calculate specifics, you have to bring it back to its whole circuit. So we're going to cross out a bunch of stuff for source dominance, right? However, to find like this current, we can't cross everything out because then we don't know what that current is going to be. Technically, the current is up here is different than those currents. But we need to bring those back in because we need those to find that current. So that is, I think those are the most important things. Also, big hint, because some students did this on one of our exams. It might not be a source dominance problem. It might just be a source combination problem. If in his thing, it does not say source dominance, that's a hint to not use source dominance. So if that isn't mentioned in the problem, don't try to use it.
Does that just make it like messy, I guess? Use sort of dominant when it doesn't say it.
It makes it messy, but then it also leads to students doing what I said earlier of trying to dominate, like have a voltage source in series with a resistor, try to dominate something else.
Oh,
It leads to small mistakes.
Getting correct.
there are times when the current source can't dominate. Because like you said,
Yes.
like in parallel like that, like parallel to the district.
Yeah. Exactly. You would have to have it be transformed. You have to transform stuff before if it doesn't directly dominate. I'm not saying that, but we're just going to start working it out. Okay, I think the easiest ones to see personally for me are the voltage sources. So what do we see first that we want to cross out?
The one on the,
Well, let's do the voltage dominance first.
yeah, E2 and then
What are we crossing out?
do Ohm's laws, so we can just do Ohm's laws and make it just the current source.
We're doing source dominance right now.
Oh, yeah.
So voltage dominates in parallel. So we can cross out that resistor.
Basically get rid of
Mhm.
of all the stuff in parallel with voltage sources E1 and E2. Then we can get rid of all the stuff which is in series with J2. Kind of. Can you take away that resistor that's in series with J2? Actually, Wait, no, we have to convert J one into a voltage source before we could do that. Probably. We have to be. So, convert it into a voltage source. And then we have R one in parallel with it.
Oh, you mean J?
Yeah, J one, J one in parallel with, R one, so we can convert that to a voltage source and basically get rid of everything along that line.
Okay,
Oh.
so I also partially, and I read the solutions before, I partially disagree with his solutions on this.
Oh.
And, but it's okay.
But what do you mean by that?
I'm about to show you.
You get different answers?
About to show you. So it says you need to preserve nodes 1 through 3. That means that you cannot get rid of this node, or this node. But Russell gets rid of that node. And then brings it back. So and it's basically just so it's easier. But whatever. We're gonna redraw it with that preserved. Fish. Okay. So this, like you said, dominates this. Does it dominate that? It does. So from VN1. There is just a current source. I am so sorry. That has just been annoying. 5 milliamps. Then we have VN2. And then what do we have here?
Just one battery. We have R6.
Exactly. So what Russell did is he got rid of this. What?
Why are you not using like wiggly line notation?
I am.
Just kind of bigger. So-
They're just messy. I'm sorry. That's I
No, you're okay. Is it just that no one can draw those like correctly?
well, it's not that I can't. I'm just trying to get through the review quicker. And so
No, you're, sorry, okay.
so
Also, it's the reason why the battery doesn't take away the resistor in node 3, that because the node is there, like you can't.
so that's the preserving the node thing. But if that node weren't there, that voltage source wouldn't dominate it anyway, because it doesn't dominate in series.
Okay.
So both of those things. And then what we're going to do here is we're going to go ahead and convert that to a voltage source, which y'all already said. So what is that voltage source equal to? Mm-mm. 4 milliamps times 100. No, it's not. 0.4. Mm-hmm.
Someone like 5,000, so like multiply.
0.4 volts. Is that what you got?
Okay, how do you turn it from fractions to whole numbers?
Control enter.
Yes.
Also, quick note. All of Russell's solutions are in decimal form, so for the sake of your TA, put things in decimal form. Because if they're feeling lazy, then they might not do it in their calculator. So this with VN1 preserved is the reduced network. So that is the first part. Now, VN1, VN2, and VN3. What is the easiest one to do?
Maybe BN2, like it's just straight down to ground, right? But that there's not like voltage really, so it wasn't.
Well, wait, actually, no, BN2 might actually be on this. But,
The M three.
I like VN3. So the reason that I like VN3 is because we can figure out what the current here is, right? And then VN3, because this is 0 volts. We can find what the voltage drop here is. And then that's going to be what VN3 is, right? Cool. Cool. So actual values, 400, 600. What is the current flowing there? Yep. 5 over 100 equals 5 milliamps. So what is 5 milliamps times 600? No, that's
It's normal thing.
is it normal thing?
Yeah.
30, 30,000.
It is times 600, right?
I see why you didn't. And cheated. That's what he did. Okay. So realistically, it's not quite that easy, and I should have known that. You would need to know the current over there too. And do a KVL. Because there's also current here, and that will affect the other
Like
current.
the one before, like 1 minus
Right.
both.
I'm pretty sure we know by KVL that the change in voltage across resistor, well, like the resistor 6, resistor 4 would have to be equivalent to 5 volts. And then the change in voltage across resistor, resistor 1 and resistor
Maybe they gave you
4 would have to.
It gets funky because there's a current source in here and you don't normally do that. But here, we're gonna do the cheating way because, and I'll explain why you can do it. So what he does,
Well, actually, but would we know the current flowing through the 1000 ohm resistor because it would be just equivalent to that current source right there?
yes,
So then we could just be 5 milliamps times 1,000 or times 1,000 ohms, which is how many volts again? 5 volts.
so,
And
But we
because,
can't figure anything out when we combine stuff, right?
mhm.
and in that case, that the change across the R4 would have to be 4.6 volts, I believe. Because we have a
Let's
0.4
do the
volt
cheating way.
current source. And
let's do it this way, okay?
uh,
You can solve it on your paper and see if we get the same result.
all right.
So we're just gonna do it like this. I'll show you why he does this. So we now have a current source in parallel with a resistor. So now, because we used source dominance here, we can get this into one loop, which makes things super duper easy. So 5 milliamps times 400. That 2 volts. Someone check me on that. Two volts. Yeah, it's 2 volts.
Oh, where?
Sorry, I transformed those.
I don't know.
5 milliamps times 400, 2 volts. Then we have 400, 5, and 600. Now, what's the current flowing in this loop?
Um, 7 volts.
Divided by,
And the 3. Uh,
so 7 divided by 1,000 is 7 milliamps, right? Okay, so now let's find V3. So it's just going to be 7 milliamps. It's the exact same thing we did earlier. 7 milliamps times 600.
So, I remember earlier you said we can't figure things out when they're transformed, but what was that again exactly, or was that?
So, okay, we can find the node voltages when they're transformed because we're not canceling anything out with this, right? We are, like, we couldn't find this current, for example, right?
Yeah,
And then we're gonna need eventually, where is it? This voltage, right?
and for those, we gotta turn it back to normal. But
Mhm.
for this no step in that.
Exactly. Because those are just equivalents. And um I
Because it's the same thing flowing into a node.
Mhm.
So it's like as if it's a box or something.
Exactly. And if we think about voltages, the current flowing in and the current flowing out are always going to be the same for this entire thing, right? If we have a voltage source, that means that the voltage drop over this, and this are all 5. So effectively, does it change with this stuff?
Yeah. Know how big the box is.
Well, no, it actually, it doesn't change. It changes how much current is flowing through each of these, but it doesn't actually change exactly. So that's still 5 volts. That's still 1 volt. And then this will eventually change the voltage over that, but no matter what, there is 5 milliamps in this loop. That's why you can do dominance. Cool. So VN3, 4.2. We have a super easy one. Can we get VN2 with that? My work clear. Can you see that that's VN2?
Yeah, but, let me know when later. So,
So you can sort of, well, we got rid of of VN1, right? So we're not gonna go that way because that's not completely accurate. But we know this and we know this, right? Voltages are just differences, right? So would you agree that VN2 is that?
yeah, the Google check not accurate.
Do we know everything there?
Yeah, we do.
So we have VN3. We can either go this way or we can go that way. It doesn't really matter. But let's just go this way, because this is how we did it on the MAME problem. That's why I'm doing what I'm about to do. So we're saying VN2 is going to be positive, and 0, because this is 0, is at the bottom. So we have a negative 5 volts here. Sorry. We have 5 volts here. Give you the answer. Is this going to be negative or positive?
Wait, I know you said, but isn't it? Oh, that's where is this where you said last time that the voltage drops in that matrix thing is like it's the opposite? So I would say it was positive normally. I guess not normally, the main one, but for this one, it's negative.
Exactly. Because we're denoting that VN2 is positive, and then we need our next thing to be negative. Same over here, positive, negative. But this polarity is the opposite direction. And so VN2 is equal to negative 5, and then is it going to be plus or minus 4.2? So what does VN2 equal? Also, please block your answers. I didn't say that. Please block your answers.
I'm not getting the correct answer.
Yeah, it's a little funky. And I'm not sure why it's so funky.
You were able to like not care about node one. What was the reason? Why are you not able to?
Wait, say that again.
Well, wait, why is it okay that we were able to like, I guess like ignore node one to figure out these other nodes? Even though it said we gotta not do that.
Because it does do the source dominance, like it should dominate that. That if we're using source dominance, that is what should happen. Because now if we put VN1 down here, that's saying that VN1 is equal to ground. Exactly.
What if we did an E shape?
And will there be E shift and I shift on the,
I really don't think so.
Like, would it be possible to do an E shift to get the current in well, by itself? And solve for everything? Or would that have changed the node voltage?
I think that's going to change the node voltages.
That would make sense.
Now, from here,
What, would you have taken points off if we could fix?
what do you mean?
E shift?
No, like this, what we, like just.
Well, no, this is the right answer.
Why is it telling us something? Oh my goodness.
I don't, I didn't make, I didn't, I don't know why. But now what we're gonna do is, just reconstruct this, and we could have found it earlier. Like when we redrew this, it's not hard because this does dominate. We're just gonna plug this back in real quick. Exactly. I know why it doesn't work the way that you're doing it right now.
Oh, wait, no, actually, I found a wrong value. That's why it didn't work. No, let me try, let me redo my calculations. I actually added zeros on that.
So I'm just putting in that 0.4 volts again, okay? Does everyone know why I'm redrawing this?
I thought you said it before, but I don't know.
Okay, yeah, I'm putting this back in here because we source transformed it before. We're transforming these two guys back into a voltage source because we're trying to find VN1.
we're making, like, putting that node back.
Yes. The reason that it wasn't happy before was because we were trying to find, we canceled out one resistor, but we didn't cancel out the other resistor. And that's not gonna be good for voltages. So when I just redrew this to find the VN1, I had to put both resistors back in there. Yes. In this. So now what we're gonna do is we know 5 milliamps are flowing through here, right? Okay, so we are trying to find VN1 from VN1 to ground, right? So we're gonna need the voltage drop over this 100 ohms and the voltage drop over the 0.4 ohms or 0.4 volts. Tracking? Okay, so what is the voltage drop over the 100 ohms? Which is, is that going to be positive or negative?
Positive, right? Is it going down?
So current is flowing that way, right?
Oh, so that, like,
So the current polarity is that.
oh, so,
So exactly, we're looking for the,
Somehow replicate that.
the current source still does dictate what the current flowing is. So he's using here, it's less current dominant. No, you're good. You're good. I also did this at the same time and I scared myself.
oh,
It's less current dominance and more just the rules of KCL of if you have a current source, that defines the current in the whole branch. So because this current source is here, the current in this is going to be 5 milliamps.
Okay, so we can't get rid of resistors in series with a code. Kind of.
Sort of. We did earlier, like we can for source dominance. Right now, we're trying to find the voltage drop over resistors and batteries. We can't get rid of them whenever we're trying to find that.
That makes a bunch of
so
sense.
these resistance that is important to adding up the.
Exactly. Exactly. So here we have 0.5, negative 0.5, negative 0.5, because the polarities are opposite.
Change anything for just on the resistors?
Yes, because VN1 is in between the two
Oh,
resistors.
it's not.
Okay, so then are we going to add 0.4 or are we going to subtract 0.4?
I just want to confirm that this is a simple circuit, right?
Simple? What do you
Like,
mean?
this is the circuit where you then reduce it down to its.
No, so this, well, yes,
We did it before to find two of the nodes, but now after that, we gotta find the node one, and we gotta unsimplify behind it.
Mhm. Because right now we're calculating VN1 and I shouldn't have erased it. I erased the simplified one. I should not have done that. That is my bad.
I saw it.
But yeah, so we said add, right? Did we say add?
No, I mean.
Oh, I guess we're getting down.
If you add, okay. It's just for,
Yeah, passive device notation.
yeah, because for batteries, it's opposite, that we kind of treat them like, whenever we're doing voltage, or we're adding potential voltage drops,
We will drop notation.
You're overcomplicating it. We know the polarity for this voltage source, right? Is that the same direction as VN1 and VN2? Is that the same thing we're looking for?
So we know that the current in this branch has to be 5
oh,
volts.
ask for that, question one more time.
Okay, so VN1, we're looking for positive to negative here.
Yeah. Well,
Is this polarity,
it's
does
the
that
same.
agree? Exactly. That polarity is the same. That's why it's positive.
Oh, and so it's not like an opposite kind of thing, just like basically follows the node. That's positive.
But actually, can we solve VN2 by basically just doing like 0.4 volts plus 5 milliamps times 100 plus 5 milliamps times 200? And then we.
Yes, but we already found it. It was negative 0.8. So that also will work. But that we would be solving for it a second time. We could have gone the other way, I think, or not, I think. We could have gone the other way, but this is kind of the order that it's wanting you to go. So what is VN1? What is it? VN. Okay, so now voltage VJ2. We are close to doing that. Here, very close. So now that we're trying to find the voltage drop over a current source, can we directly ever in our lives find the voltage drop over a current source without a multimeter?
No.
Mm-mm. We mathematically will not know it unless it's a non-ideal and it has inherent resistance. We don't know what it's going to be because it doesn't have a set resistance. It depends on the rest of the circuit. So to find this, we have to bring everything back in.
How did we make the original circuit redrawn?
Where you can say,
How do we find the change across ours, across the 600 ohm resistor again?
so we simplified it. We simplified it down to this,
Okay.
and then we
Oh,
made those,
that makes sense.
and that's where we got this circuit,
And that preserves RN1 and RN2, right?
VN2 and VN3.
Yeah, the answer.
Yes.
Okay, thank you.
So we don't actually have to draw the entire circuit because we know what VN1 is and we know what VN2 is, right? Technically, not technically. All we need is what's between those two voltage nodes to find that. So I'm going to draw most of the circuit, but I'm not going to draw.
Oh, what are we finding them between nodes 1 and 2? Oh, that whole thing.
Yes. We're finding that. So do we need to draw the resistor and the voltage source, or do we just need to draw the voltage source?
Oh, we're finding voltage, so no, right? We just.
Yeah, I don't think we need to keep, we don't need to keep the resistor and the voltage because the voltage across both of them will be the same anyway.
Exactly. Because, and it's very important, because we're looking for the voltage here, all we need are the voltages in that section.
Do the same size paper, like it'll be this size too.
Oh, God.
You get scratch paper.
Okay.
You get scratch paper, you show all your work, we grade your scratch paper. Well, I don't grade.
Okay.
So do we actually need either of those? Either of these branches here? Because this is negative 0.1. And this is negative 0.8, right? So we know that from there to there needs to add 7 volts.
Oh, what's that?
Yeah, sorry. Do we know what the voltage drop over this is? Can we find that?
Yeah,
What's it gonna be? Mhm. One. Two,
And then we have a 1 volt drop,
mhm.
0.1. So that's 1.1. But we need a 0.7, so, wait, does that mean that the?
No, it should not, yeah, it should not be. one.
Yep.
Does that mean that the current source has a voltage rise of,
Yeah, so very, yes, he does this a lot. He will ask for a voltage or a current in the opposite direction that it actually is. All that means, if you think about it in the practical world, is if you put your multimeter the opposite way. Exactly. So you might not know that it's going that way. So you just arbitrarily put your multimeter with this being the positive and that being the negative. Obviously, we're looking at the circuit and we know that that's not what it's going to end up being, but it is asking, write the answer in what it's asking you.
Not in like what it actually.
Correct. Your answer will just be negative. So all a negative voltage means is that the signs should be flipped, right?
But like, so if we,
Yes.
so the answer would be, it would be negative voltage, if we put it, that's wrong. Like, if you make it positive, that's wrong.
It needs to reflect what,
What the math shows.
yeah. that. So do we want to say that -1, well, actually, no, which is bigger, -1 or -8? 0.1. Yeah, so we're gonna do positive and negative. So this is gonna be a drop, right? So that's gonna be -0.1 plus 0.1 plus VJ2 plus 1 equal to, or
No, it should be negative.
actually, yeah, wait, -0.8. Or we could just put plus -0.8 and then equals 0.
yeah. Plus, no, minus -0.8. That's terrible.
Oh,
It-
why is
Uh,
it minus negative instead of just plus negative?
because we're looking for the voltage, because like, remember, it's VA minus VB is what we're looking for. Or it's not equal 0. This is what we're looking for. We're looking for VA minus VB, right? And so,
Wouldn't that be 0.8? Right. We have all the stuff in the middle, the voltage rises and drops combined is equal to 0.1 plus that is equal to -0.8.
yeah, there's different ways that you can write it, and I think I'm mixing up different ways. It's my bad. Sorry. Let's do it this way. This is what makes sense, right?
Yeah.
Okay. So what is that? -0.1 plus 0.1 is 0. So VJ2 plus 1 needs to equal -0.8. What is VJ2? Exactly. So that means that VJ2 is equal to -1.8. Does that make sense that it's negative?
They could just assume it's like a battery or something.
Well,
Well,
it's a current source.
yeah,
So
not a battery.
yeah, So it is actually supplying voltage. So it is a correct sign. The actual sign is this way, which is how we like drawing our current sources.
Yeah. That, so the way it's supposed to be, it would cancel out, but it would be like negative.
Would
Exactly,
just look like an active device state.
passive.
But like the actual way the current's moving is this way.
Yes. The voltage rise is active device. Voltage drop is passive device.
Is it visible by surface?
Right, which is why it's active. We were saying if it was the other way,
So you have it.
it would be a passive device.
So then wouldn't we have everything else be an active device then?
No. Everything else is also a voltage drop here. Like, look, this is a voltage drop.
Yep.
And then the way it's written, this is a voltage drop.
Yep.
And this is a voltage drop. This is basically saying that all of these things are passive. But really, it's passive, active, passive. So actually, the battery is actually kind of passive, but that's besides the point. We have one more thing we need to do. We need to find the current. How do we do that?
You do the same thing. No,
Well, okay,
oh
wait.
wait, can we turn the?
We know that the difference between the voltage for that one is 5 volts between VN1 and V2. Therefore, the voltage going across the resistor has to be equal to 5 volts. We also know that there's a current source over there. So the current going, so the current going through
So let's,
actually, wait, also, do we know the current going from VN1 to VN3?
no. But we know the current flowing from VN3 to ground, right? If we know the voltage.
Yeah, so that current must be flowing out of the node right beside node 3.
Mhm.
Which means that we can use KCO to figure that out by basically finding out what the necessary voltage across the, or necessary current across the resistor to produce a 5-volt difference is.
Yes.
We just subtract 2 from that.
Mhm.
And
So what is the current flowing there? It's, we already
that's-
found the answer. It's 7 milliamps. It's from this, but if we wanted to solve it again, it would be 4.2 divided by 600, which is 7 milliamps. So 7 milliamps needs to enter, and 7 milliamps needs to leave. So we know that there is 2 milliamps. I'm gonna fix this now. There's 2 milliamps flowing that way. Do we know how much is flowing on that resistor? Do we know the voltage drop?
Yeah, we know the voltage drop is 5 volts, but they're both 5.
Yeah, I think current.
It's 5 milliamps.
Mm-hmm.
So for the current going across the resistance 0.
Which, not the resistor, the
Or not the
battery.
resistance, voltage source is 0.
Yeah. Because the because okay, which way is the current flowing though? So it's a voltage drop this way, right? Does current flow in the negative or into the positive for a resistor?
No, goes to the bottom.
So if we come over here, right, it always flows in the positive and out the negative. So here, it's flowing that way, right? Because 5 volts is dropping that way. So it's actually 2 going that way and 5 going the other way. So we need 7 equal to 2 plus 2 minus 5.
Something like 11. Or negative 11.
No,
Plus 5 minus 2 is 7.
But we haven't been,
Right? It is.
no, because, okay, 7 needs to be flowing from here to here, right?
Yeah.
Is that 5 flowing that way? So it's gonna be minus.
So that equation's right.
Yeah.
Okay.
but IE2 is depicted as going in the opposite direction than the way we needed to go, basically, so it's going to be negative.
Is that kinetic?
Mm.
Is it going right? Between left and right?
Mm-hmm. Yeah, sorry, I drew the way that it's actually gonna be going.
Oh.
So minus IE2. No. Okay. So to do KCL, we need to find which direction it's actually flowing, right? So
Oh,
we're just gonna call it X for right now. 7 milliamps, 2 milliamps. All over the place, I'm sorry. Equal to X plus 2 minus 5. So solve that. What should our current through this battery be?
So 10 minus 2, 7, 5, plus 5 is 7.
Mm-hmm.
um,
Mm-hmm.
oh my God.
So which way should it be flowing now?
Okay. That's the right.
Mm-hmm. So realistically, there is 10 milliamps flowing that way. Yes. So I don't like how it's written up there. I'm just gonna draw it out one more time. Sorry. Minus 5. X. So X in that direction, we already said this, 10 milliamps. And then IE2 is opposite direction. Negative 10. Okay.
Well, you said you can find a video that they can use, right? Like I can upload the videos.
Yeah.
Okay.
There should be something in the Discord about it.
Yeah, but
Okay, cool. The IEEE or the UTA undergrad Discord. But okay, I think that's. Do we have any other questions before I finish? It's early in the morning, so you can do the day before.
Yeah. So we're gonna have to give our ID, because I kind of need that to get back on my dorm.
Yes, you can. It's Tuesday, Thursday. You know what? Someone should probably be here, but we can talk about that after. Any other questions? Okay. Friday.